In this video, we'll take a look at some more useful algebraic properties of the logarithm function. Let's suppose that a and b are both written as powers of 10. What can we say about the log base 10 of a times b? If I think of those two numbers as powers of 10, then I can combine their exponents. Totally disregarding the logarithm for a moment, multiplying together two numbers that have the same base is the same as adding their exponents together. So I've taken 10 to the x times 10 to the y and combine those to 10 to the x plus y. But now I have the log base 10 of 10 to a certain power. And we've already seen that log base 10 and 10 to a power cancel each other out. So I'm left with only the exponent x plus y. But another way to write x is the log base 10 of 10 to the x. And another way to write y is log base 10 of 10 to the y. 10 to the x is the same as a, and 10 to the y is the same as b. So I can write that as log base 10 of a plus log base 10 of b. So if I look at just the first and the last line of this derivation, the log base 10 of the product of two numbers is the same as the log base 10 of the first number plus the log base 10 of the second number. A shorthand for this might be that multiplication on the inside of a logarithm turns to addition of two separate logarithms. How might we do this for division? I can start the same way and say that a is 10 to the x and b is 10 to the y, and I can combine the exponents just like I did before. Here I'm dividing two numbers that have the same base, and so I subtract their exponents. So regardless of the logarithm, I'm just looking at 10 to the x divided by 10 to the y, and that's the same as 10 to the x minus y. And again, now I have log base 10 and 10 to a certain power, so those cancel and leave me with only x minus y. Now I can finish with the same logic as before. X is the same thing as log base 10 of 10 to the x, y is the same thing as log base 10 of 10 to the y, and 10 to the x and 10 to the y are just a and b. So in this example, division inside the logarithm turned into subtraction between two logarithms. For this one, let's let a be written as a power of 10, and c is just any real number, and we don't care how to write it as a power of 10. What can I do with the log base 10 of a to the power c? If I start by writing a as a power of 10, notice I have 10 raised to a power, and then a raised to another power. I can combine these by multiplying the two exponents together. And now I'm in a place where I can do the cancellation. I have log base 10 of 10 to a power, and so I'm left with only the power. And then continue with the same steps as I've used before. X is log base 10 of 10 to the x, and 10 to the x is just the same thing as a. So the result was that log base 10 of a to a power is that power times log base 10 of a. In short, the exponent comes out in front and multiplies by the logarithm, but the base stays inside the logarithm. Here I've just summarized those three laws again. We use log base 10 to make our examples a little bit easier to follow, but these laws are true for any base. These laws are useful for expanding and combining logarithms. Expanding a logarithm means to write a logarithm with a complicated argument as a combination of many simpler logarithms. And combining the logarithm is just the opposite. You combine many simple logarithms into one complicated logarithm. Since the expansion of the logarithm undoes the operations that are occurring inside the parentheses, we need to perform the expansions according to the reverse order of operations. So what I mean is this. If I knew the values of a, b, and c, and I just wanted to evaluate this, probably what I would do is multiply a by b first, then take the cube root of c, then finally divide the resulting numerator by the denominator. Since the division was the last operation to take place according to the order of operations, then it's the first operation I should be undoing by the expansion of logarithms. So if I apply the law that has to do with division, it said that the log of something divided by something else is the difference of those two logs. So I have log of AB, that's the numerator, minus the log of cube root of c, which is the denominator. Now I have two slightly simpler logarithms, and I can see if I can expand those further. If I look at just the first one, I have the log of a times b, so I can apply the multiplication law and write that as the log of a plus the log of b. And then the cube root, I have to remind myself that cube root of c is the same as c to the 1/3 power, and I can use the logarithm law about exponents to say that the 1/3 power should come out in front of the logarithm. so that the log of cube root of c becomes 1/3 times the log of c. Now each of these logarithms is as simple as they can be, and so we can't expand any further. If I want to combine these into a single logarithm, this time we want to perform according to the order of operations, because we want to combine these operations into a single logarithm. We're not undoing anything. The first thing I could do is clean up both the individual logarithms by pulling the powers inside. And so the times by 3 on the first logarithm would be the same as log of s cubed. And the times by 1/2 would be the same thing as having a 1/2 power on the inside. And so I've written that as square root. Now I have one logarithm minus another logarithm. The division law says that the subtraction of two logarithms is the same as dividing their two arguments. So the log of s cubed minus the log of cube root of t plus 1 is now the logarithm of s cubed divided by square root of t plus 1 as a single logarithm. We can also use these laws to evaluate logs in strange bases. Your calculator probably only has log base 10 and another one called natural logarithm, which we'll discuss later. What if I wanted to evaluate logarithm base 5 of 11? Evaluating log base 5 of 11 is the same as solving the equation pi to the y equals 11 for y. We could use a logarithm to try and get y out of the exponent, and we may as well use a logarithm like base 10 that occurs in our calculator. On the left-hand side, the power rule for logarithms would say that the exponent of y comes out in front, and I'm left with log base 10 of 5. And on the left-hand side, I have log base 10 of 11. If I divide both sides by log base 10 of 5, then I've isolated y, and I know that y is log base 10 of 11 divided by log base 10 of 5. Now, it looks complicated, but those are both just numbers. I can plug both of those into a calculator and divide and see that y is about 1.49. If I wanted to check this, I could go back to the first line and say that 5 to the 1.49 is about 11. So 1.49 is roughly the exponent I would use to write 11 as a power of 5. This trick works all the time, and it's called the change of base formula. If you want to evaluate log base b of x, probably b is some unfamiliar base. You can rewrite that as log base a of x divided by log base a of b, and here you would choose for a more common base, probably log base 10 or the natural log that appears on